and gentlemen, good morning. Welcome to this session dedicated to the European Research Council AROMA-CFD project. I would like to welcome also all people connected in streaming and also, of course, to the audience in this room. Today, we would like to introduce some of the activity that we are carrying out with this project by presentation given by younger researcher on the project, but also it's a very great pleasure to me to have also a dialogue with Professor Alfio Quarteroni. Good morning, Alfio.
Good morning, Luigi. Thank you for inviting me.
The title of this session is Computational Methods in Fluid Dynamics with applications in biomedicine, environment, and industry. And this session is in the framework of breaking frontiers in science and knowledge here at ESOF. I would like to introduce just briefly Professor Quarteroni before starting this dialogue, saying that Professor Alfio Quarteroni is Professor of Numerical Analysis at Politecnico di Milano and Professor Emeritus at École Polytechnique Fédérale in Lausanne. And he has many titles, but I would like to mention two very prestigious ones. He's a member of the Italian Accademia dei Lincei and members of the Istituto Lombardo Accademia Scienze e Lettere Milano. And it's very difficult to introduce you, but I think that I could just say that you are one of the leading applied mathematicians in the world and an established innovator. And we are very proud of having Professor Quarteroni with us, and of course, thanks also for your availability. I would like just to warming up the room and the session with starting a dialogue to introduce also the main topic and the main theme of this session. And I would like just to start with mathematics and applied mathematics. We are knowing a very nice season in terms of rediscovery of this basic science discipline. It's an old discipline, but with a very modern appealing. Would you have expected such a new season for mathematics? And why this new spring season in mathematics, also with so important development in mathematical modeling? Professor Quarteroni.
That's a good question. Well, first of all, good morning to everybody. Well, I have to confess that when I was a high school student, we are actually, in that generation, we're always dreaming of conquering the space. You know, there was the first man on the moon, and we're all dreaming that sooner or later we would have been able to use rockets and shuttles to travel the space. So the new frontiers were supposed to be aerospace, which has actually been a frontier, but the real revolution, as you know, was made by the computers first, so the microelectronics and the computers first, and then by the web in the mid-90s, and then more recently by the social media, the fact that we are all globally interconnected. And those revolutions have had indeed a major impact on the development of mathematics for several reasons, and I will just mention here maybe a couple of them. The first one is that in the 19th century, there have been a great achievements in mathematical discoveries due to the giant people like, say, Maxwell, Laplace, Navier and Stokes, and Schrödinger, and many others. They gave fundamental equations, they gave fundamental laws. And those laws have been basically silent for many years until when we had big supercomputers that enabled the numerical solution of those problems. So this is the big flourishing of mathematics, applied mathematics, numerical mathematics, scientific computing. And for the first time, we have been able in this, say, past 40, 30 years to attack those type of fundamental equations and produce results, and then having an impact on in the real society. So this was the big blooming. And the second one, as I was saying before, is is due to the fact that we have the WWW and we have social networks, and this basically opened the way to discrete mathematics this time, not continuum mathematics as before. Discrete mathematics because we need a page ranking and we need good classifiers to rank pages, and therefore we need to explore combinatorial optimization on the big gigantic databases. We need, you see, optimizers to have navigators because we want to be able to use our cars and travel from place A to place B without too many troubles. And of course, we need to be interconnected through the social networks. So we need advanced linear algebra to explore the graphs, to explore the big networks. So this has been marking a revamping on discrete mathematics. There's been a lot of new mathematics that has been created. And of course, now the impact is terrific. We know that we have mathematics embedded into our several phones. We have algorithms, efficient algorithms everywhere. And I guess those have been the major landmarks that enable mathematicians and mathematics to become so important and so determinant in our daily life. So it was very difficult to expect that 30 years ago, 40 years ago, but even 25 years ago, I'd say.
Yes, yeah, but that's great that this season is still continuing with many new frontiers to face and to advance.
I guess the perimeter is always moving, right? It's a continuously expanding type of surface, and mathematics is going to be at the interface of this advancement and to be absolutely decisive.
It's a sort of diffusion transport process that we will see later in the presentation. And I would like also to introduce the second topic of today's session, which is related on the fact that we are presenting and discussing an European Research Council project. And could you give us your thought about ERC, opportunities, high risk, high gain projects? Your perspective is quite important because you have been awarded to advanced grants, to proof of concept, and of course you have served and coordinated also for some years, and maybe many years, should be more correct, the panel PA1 in mathematics for consolidator grants at the European Union.
Yeah, well, I've been involved since I guess, very beginning, because now it's 13-year-old, this ERC program. So I've been in the panel since the very beginning, and I've been benefiting myself, as you're saying, by grants, important grants. I think this is a very distinguishing operation of Europe. Finally, we have something to be proud of, right? And this has really marked a very important step in international research, and I think we can safely say that all the countries are now really appreciating and somehow trying to imitate this structure. Well, let me say that for me, this has been from the inside, being a chair of a panel, a very important experience, because I've seen so many young, brilliant researchers who have been able to get this grant, even people coming from less favored countries, from universities that are not as prestigious as Oxford, Cambridge, and see several others in Europe, and still being able to establish themselves as researchers and creating a very important groups and disseminating their knowledge and creating really a drift. And I guess you yourself, Gianluigi, you are one perfect example in this story, and also the group that you have created, still creating with the AROMA-CFD project, is there to witness that you can make great things with such grants. I think that the distinguishing feature is that the European Research Council has always wanted to put a prime on curiosity-driven research and funding these projects with, let me say, important money, which is today very difficult to have on individual research. You know, the trend now is not only the European level, but generally speaking, in worldwide, is to try to put substantial money on network of researchers and on proposals that are really driven by strong applications. This is important, of course, but it's also important to cultivate the individual minds, individual excellences, and the brightness of people, and to create the condition that this excellent research will sooner or later end up with having a very important impact also at the application level. I think this has been the roadmap of the ERC, and I'm very happy to see that this has produced fantastic results. And if you go and count the number of Fields medals or Nobel Prizes that then have been, somehow come as the result of these investments, well, this is something our continent should be proud of, I have to say.
Yeah, it's been a great opportunity for the creation of the group, but also to give opportunity to younger scientists also to stay in Italy for the starting of their career. So we will
absolutely.
See
this has created really the perfect environment for people to be embedded into important groups, doing excellent research, and also trying to make this compatible with the development of their own life at a personal level. I think this is something that you should be very grateful to European Research Council. Absolutely.
Yeah, we are. And a last warming up question, then the dialogue will continue also when the younger scientists will have introduced new topics and also new critical issue. But you are an experienced innovator. Innovating with mathematics is your motto in your career and also what you have created at Politecnico di Milano. How would you describe innovation capability and innovation process?
Okay, thank you for your kind words. Well, I don't know if I can share some slides.
Sure.
Maybe this could be useful. Well, first of all, let me say that I believe that well, I don't know if I'm an innovator, but to innovate with mathematics, we need to develop the knowledge of mathematics. So I strongly believe that innovation and education should be strongly interconnected. We have first, before innovate, you have to create the condition to innovate. And I'm personally convinced that you have to invest on basic knowledge. So this is one example of what we did in Italy, and I'm insisting in showing what we did in Italy because, as you know, it's not always so easy to create new things in our country where there are fantastic opportunities and very brilliant minds, but sometimes the environment is not as, how to say, favorable as in other countries. So we decided in Politecnico di Milano well, 19 years ago indeed, to create this new branch of studies, this new track, which is called Ingegneria Matematica, Mathematical Engineering. And because we wanted really to create a branch where mathematicians could develop in a perfect synchrony with applications and in a strong synergy with the external world. So in 2002 created the MOX, which is a laboratory, so a research laboratory, and MOX has then created so many contacts with the external environment to allow people, students in Engineering Mathematica, to work on projects of real applied interest. Then in 2010, MOXoff was created as a spin-off of MOX, and then in 2016, Math and Sport was created out of MOXoff. So you see it's a kind of vertical developments from basic education to fundamental research in university environment to translational research at the engineering level. Now, just one little comment on the mathematical engineering to say that it has been, in my opinion, a very successful story. After 1 year of graduation, basically all the people are employed, and these are statistics over the last 15 years. Most of them are employed in Italy and around 15% abroad. And among those who are employed outside the academic environment, you see here the distribution. So 31% in banking and insurance, 31%, roughly speaking, IT consulting, and then 10% in ICT, and then 20% in consulting, generally speaking, and also in the research and development branches of industries. And several of them, so I would say about the at least the 10 to 15%, then accepted very prestigious PhD positions everywhere in the world, and now many of them are professors also in very good universities. Let me say a couple of words on MOX. Well, MOX has many academic collaborations with many universities. We see here some of them, and many industrial partners. I would say order of at least 100 industrial partners from every field, which tells us that mathematics is really transversal. So the average funding is 1.2, 1.3 million per year, which is not big money, generally speaking, but for a mathematical department, for a mathematical institute working in Italy in a mathematics department, this is substantial money, I have to say. And most of this money has been used for keeping young students and creating opportunities for young students for a PhD track or for, say, postdoctoral track. So I think we are very proud of that. Now, MOX-OFF is a bridge between MOX and the external environment. So those are some top customers. Now, after 10 years of operation, there are more than 200 projects and more than 100 customers. Now 30 employees, full-time employees, and those are, say, at least half of them have one third of them a PhD, the others have a master in fundamental sciences, so mathematics, physics, computer science. And MOX-OFF has created 2 spin-offs. So I think MOX-OFF shows that you can innovate also in Italy. You can create structures that allow, say, bring people to operate in an environment which is very contiguous to the academic environment, and still developing a project that are of relevance for the industrial world. And of course, this is a private company, right? So the salary should be paid on the budget. There are no external support. So we are proud to say that we can provide a very excellent environment to people who are working on the basic field of mathematics, I would say, data science, modeling and simulation, and optimization. So I think this is a way where mathematicians, applied mathematicians, can find their home if they are interested in really creating a translational mathematics environment. I don't know if this answers your question.
No, thank you for
just one example.
No, it's a very wide presentation also about perspective, and also the numbers are quite significant for Politecnico. I would like just to say that also here we are lucky because we are hosting many Politecnico di Milano alumni, and also some of them are coming from mathematical engineering. You will see also a presentation from Francesco Ballarin, one of them. So it's, of course, it's a great achievement for at the national level first, and then at the international one. So now it's a very useful introduction also, since the audience in the room is full of very young people and scientists that they could know about this development in Italy, also to have a more optimistic view about the situation also of Italian research.
Yeah, we need it.
So thank you. Now,
to be more optimistic, I mean.
Yeah, I think that, yeah, I would like that after this session, we are going home more optimistic, and also maybe with some dreams in our pockets to try to build in the future. So I now leave room to some young scientists introducing also the AROMA-CFD project, and so we can maybe start with the slides presentation. And before leaving Giovanni Stabile space for his presentation. Could you move up, please, to the next slide? Could you? Thank you.
Could I stop sharing?
Yes, please. So this is the AROMA-CFD group at SISSA MATLAB. So we are SISSA International School for Advanced Studies based here in Trieste. SISSA MATLAB has been established 10 years ago in October 2010. And this is also the reason why I'm grateful and proud to have here Alfio Quarteroni, since Professor Quarteroni has been the director of the scientific committee for establishing this new idea at SISSA. At the time, the director of SISSA was Stefano Fantoni, now is a champion of ACE of 2020. And then these adventures continue with the direction of Professor Guido Martinelli, and now with the direction of Professor Stefano Ruffo in terms of the direction at the school level. We have grown, so thanks also to 2 European Research Council grants. One is an advanced grant by Professor Simone, who served also as SISSA MATLAB director, and of course the other one is the AROMA project that we are now focusing. So I would like also to thank Alfio, since also I think that also SISSA MATLAB is bringing your DNA in terms of innovation and in terms also of scientific basic research that we are conducting. Now I leave space to Giovanni Stabile, and he will introduce the main topic of the project. So an introduction to computational fluid dynamics.
Okay. Thank you, Gianluigi, for the introduction. I'm one of the researchers working within the AROMA-CFD project, and today I will talk about computational fluid dynamics, in short CFD. And as you can understand, is one of the foundation of the AROMA-CFD project. And I will start saying basically what is CFD, giving you an introduction also historically. And historically, we were using more experimental fluid dynamics and analytical fluid dynamics. On the right of the slide, we have a sketch from Leonardo da Vinci that much before the discovery of the equations that were modeling fluid dynamics problem, started to study the behavior of flows. And basically, his approach was to build and test models in order to understand and predict the flow behavior. And then, after, let's say, Navier, Stokes, and Euler, and many other researchers, we got a better understanding about what were the equations modeling fluid dynamics problem. And we could, let's say, analytically solve those equations in order to have the flow characteristics in every point of our mathematical domain. Unfortunately, the solution can be found only on a limited set of simplified problems, and that's why we need CFD. This is really an oversimplified workflow of CFD, and where we start from the definition of the physics of our problem. So we have to define whether the problem is viscid, inviscid, incompressible, compressible, and so on. And this permits us to define a set of equations, like the Euler or the incompressible Navier-Stokes equations. And then we can translate those equations in a language that can be understood by a computer, selecting a suitable discretization technique, like finite differences or finite volumes and finite elements and so on. And to define a computational domain and to resolve those set of equations using the help of a computer, because usually the number of equations that we get from this discretization is really high. Then we cannot, let's say, solve them using just pen and paper, and we have to resort on a computer to solve those set of equations. And I will try also to convince you on some of the advantages of CFD with respect to experimental activities and other type of studies to understand the flow behavior. So with respect to, let's say, experimental activities, it's easier to change parameters. On the left, we have a model inside a wind tunnel. And of course, in case we would like to test a new geometry, we would need to recreate completely the model. And we don't have to do this in CFD because everything is in a computer. So we can easily change the parameters of our simulation. And it's also easier to take somehow point-wise investigation of the flow characteristic in every point of our domain without placing a possibly really expensive sensor. And also we can simulate some experiments that cannot be directly reproduced or measured, such as cases with hazards, like the simulation inside nuclear reactors, or cases with explosions. Of course, we cannot place some sensors there, but with CFD this is possible. And we also simulate cases that have somehow scale problems, so that cannot be reproduced with an experiment, like the flow around buildings or simulations regarding weather forecasts. And you will see more also from other researchers in my group. That's, let's say, the idea, the starting point of a CFD simulation. As I mentioned at the beginning, we have, first of all, to define the physics of our problem. So to define whether the problem is viscid, inviscid, laminar, turbulent, compressible, or incompressible, plus some other complexities, like if we have some chemical reactions or free surface flows, that some additional thermal effects and so on. And this permits us to define the set of equations which are mathematically describing our problem, like, for example, the incompressible Navier-Stokes equation or the Euler equations. And once we have the governing equations of our problem, we can select a discretization technique and to produce a computational grid, like the one showed in the slide, which is the computational grid of a set of buildings where we want to study the flow behavior around those buildings. And once we have the computational grid, we can translate our set of algebraic equations into a language that can be understood by a computer. So we can write everything in a computer code in order to solve those set of equations. Here I will show some of the applications where CFD is used and where we have used CFD also together with some industrial partners, both in the region also and outside the region and outside Italy. A really good example, also because we are here in Trieste, is coming from naval and nautical engineering, where we can use CFD to predict the flow behavior around hulls, and also to use that in order to optimize the shapes of ships to reduce, for example, the fuel consumption or to increase the comfort on board. But we can use CFD also to model industrial problems, like the one on the left, which is a simulation of a glass furnace, or machines for steel production. So it's a really versatile tool. But other examples can be found also in automotive, like if we would like to optimize the shape of a car in order to increase performances or to reduce, again, the fuel consumption, or also in aerospace applications to, again, optimize the shape of the wing of a plane in order to increase the efficiency of the plane itself or the comfort on board. But we are not only talking about industrial applications, and you will see something more also from other researchers. We can use CFD also to simulate biomedical problems in order to provide the medical doctors with tools which can help them in order to take decisions, but also in environmental sciences, for example, for weather prediction, or in civil engineering to, let's say, understand the forces acting on structures, or to predict the flow around buildings in order to understand the comfort inside the buildings, and also to study the forces acting on them. The workflow that I have presented so far is, let's say, well established for laminar flows, so everything is working quite well in laminar flows, but for turbulent flows where we have a really chaotic response and we have really a lot of different scales involved, usually there are additional complexities and we need to slightly modify our computational model in order to add some stabilization strategies in order to account for the unresolved scales and both in spatial and temporal unresolved scales. So we need somehow to add some additional tricks to our simulation in order to make it working. Let's say, as you may have understood from the set of examples that I have shown, state-of-the-art CFD solver now reach the maturity such that they can simulate a really wide range of fluid dynamics problems. However, as you will see in also from other researchers, there are still some cases where standard discretization techniques are not affordable because they are too much expensive. Like cases where you have many query problems. For example, when we want to perform shape optimization, we need a lot of different geometries to be tested, and one simulation can last also for days. So if you want to test, I don't know, 1,000 different shapes, of course the simulation time may be really long. So we need somehow to develop some methods to increase the efficiency of standard discretization tools, but also cases where we want to have a really limited computational time, like in real-time control. When, for example, I want to understand what is happening around a plane while it's traveling. So we really need a limited computational time, or when we have a limited computational power. So when we want to solve those simulations on devices with a really limited computational time, like laptops, embedded system, or smartphones. So as you may understood, there is the need for the development of tools and methods that can help to accelerate standard discretization techniques for fluid dynamics problems. And you will see that in the next presentation. Thank you for your attention.
Thank you, Giovanni. There are microphones in the audience, but there is also the possibility in streaming to ask questions, since we have an iPad where we can have a question thanks to a chat. So feel free to ask a question also. And now we change the speaker on the podium, and I go to take the iPad. So we continue with Francesco Ballarin from SISSA, introducing the reduction part of the project, and of course also some important development in open source software. Open is one of the team also of ESOF, European Science Open Forum, Open Science Fair Future. So we would like also to stress on the fact that also on the European Research Council project we are producing open source software. Thank you, Francesco.
Thank you for the introduction. I am Francesco Ballarin. I am an applied mathematician coming from Milan. I have got a bachelor and master degree in mathematical engineering at Politecnico di Milano, focusing in particular on numerical analysis and scientific computing. I pursued a PhD at MOX, at the Department of Mathematics at Politecnico di Milano. And the topic of my work there was on reduced order models for computational fluid dynamics in patient-specific hemodynamics. After completing my PhD, I joined the SISSA MATLAB group here in Trieste in January 2015. Thanks first, for the first couple of years, to an Italian national project among the research projects of national interest, and afterwards thanks to the ERC AROMA-CFD project. I currently am an assistant professor in numerical analysis here at SISSA in Trieste. The topic of my presentation will be a short introduction of reduced order modeling, which has one goal, and I will try to summarize in this slide the main goal of this variety of techniques. Let me start giving you an example. For instance, consider the video that you have on top of the slide. This video could represent the airflow in this room, for instance, if we were to turn on the air cooling system. And maybe we, for several reasons, we might be interested in considering, in evaluating how different operating conditions affect the air circulation inside this room. This is a fluid dynamics problem. In this case, the fluid is the air. And it's, more specifically, it's a parameterized fluid dynamics problem. And there could be several parameters of interest. For instance, one parameter of interest could be changing the temperature that we set in the control panel of the air cooling system, or could be the number of people that are seated in this room, or other possible example could be the shape of this room. Changing all of these possible parameters, of course, would require carrying out a new fluid dynamics simulation, and this is usually done on high-performance computing facilities. Unfortunately, as it was already mentioned in the previous presentation, these simulations are usually expensive, and thus the goal of these reduced order modeling techniques is to obtain a faster computational platform that could be employed on tablets or smartphones for real-time computations. There are, even though the name of the field is one, and the goal is somehow one, there are several possible paradigms. All of these paradigms somehow share these two common steps. In the first step, we run a few simulations and extract the most relevant flow patterns, such as the ones that you see on the left of the slide. And in the second part of the method, we combine such flow patterns to analyze the solution corresponding to any new parametric configuration. And it's in this combination that the different methodologies differ. For instance, one option could be to rely only on computational data, such as several data fitting techniques, or to be relying on a combination of computational data and physical insights, such as the reduced basis method, which is one of the key topics of the ERC project. There are several possible ways of making use of a reduced order model. In particular, one of the first options is in a setting of data assimilation. In the case that we have some data, for instance, experimental data from measurements, let's go back to the example that I gave you before about the airflow inside this room. There could be some sensors that measure the temperature inside this room. And we would like to use the mathematical model and more specifically the reduced order model to assimilate such data into the mathematical formulation in order to make the mathematical formulation such that it is a better and more accurate representation of the reality. And one of the key issues that is one of the key motivations for the project is that data assimilation usually requires comparing different parameter values, so different configurations, or even in some cases, carrying out some optimization processes. Another possible topic of interest is uncertainty quantification, and is again related to the availability of data, and it is of relevant practical interest in all those cases in which the data that we are provided are uncertain. For instance, because of measurement errors. In those cases, we need to quantify how errors in the data affect the solution, and especially for either the most probable cases or for the ones that carry the most risk, for instance, associated to failures or breakdowns. And again, these uncertainty quantification problems require a simulation on an entire range of parameters, not only for a specific configuration or parameter value. And in both of these two cases, data simulation and uncertainty quantification, there is usually a benefit from a faster computational platform. And it is with these motivations that the AROMA ERC project has been conceived and is currently running. The AROMA-CFD ERC project was awarded to Professor Gianluigi Rozza at SISSA MATLAB. Is funded by the European Research Council and is running from 2016 to 2021. And thanks to this opportunity, the group, the SISSA MATLAB group here in Trieste, has been capable of attracting more than 20 researchers from Italy and from abroad. The project is focused on reduced order methods for accurate and reliable simulations at greatly reduced computational times for real-world problems, and is somehow organized in 4 tasks. The first task is related to the development of the methodology. The second task is related to applications. The third task is concerning the development of open source software libraries. And the last and fourth task is on research dissemination, training, and networking. You will hear afterwards from people involved in the project, and they will talk mainly on tasks 1 and 2. And in the next few minutes, I will focus on task number 3, concerning the open source software development in the framework of the motto of this meeting about open science. At the SISSA MATLAB group in Trieste, we develop high-quality open source software libraries that can be freely employed and extended by anyone around the world, and are now the basis of teaching activities, collaborations, and projects with academic and industrial partners. These libraries provide an high-level integration of the newly developed reduced order methods with an already existing computational pipeline in order to propose to use all the developments that have been carried out in the ERC project as an add-on on top of the already existing computational pipeline that, for instance, our industrial partners already have. And among the deliverables for students and for partners, we have the Argos web server, which is an online platform. And you have in this image a video that we use for the training of new students. This is a video of the simulation of a computational mechanics problem. And you see how changing the parameter affects the resulting solution. And we also have a dedicated platform for collaborations with industries and clinicians. For instance, in this case, you have the Atlas computational platform for the study of a patient-specific flow in hemodynamics. This, thanks to the reduced order methodology that we develop in this project, we believe that we can improve the availability of mathematics in applications in industrial, medical, and applied sciences setting. And in the next contributions, we will hear more on this topic from people involved in the project.
Thanks, Francesco. And before moving to the next speaker, I would like to ask Alfio a question about fluid dynamics. The only branch of classical physics without a general theory due to several aspects not completely understood, mainly in turbulence phenomena. And which is your opinion now about computational fluid dynamics and its future, and also maybe turbulence? An old-fashioned discipline from last century, or do you think that thanks to artificial intelligence, meaning from machine learning to deep learning, we could give more fresh air to the discipline, in view also of the increasing role of computational scientists, computer scientists, and of course also computer science?
You said everything, basically. Well, let me say that, but this is a very personal point of view. Since several years now, we are not really observing major achievements in the field. I mean in the field of turbulence, in the field of understanding the basic behavior, basic fluid behavior, which is governed by Navier-Stokes equations. And this, I think, is due to two different factors. From a theoretical standpoint, is due to the fact that there are still, as you know, fundamental issues to be understood about Navier-Stokes and of course, this is still an active field of research for many brilliant mathematical minds, but not really major achievements have been made in the past few years, I have to say. So the theory is somehow stacked. Of course, there are achievements, there are improvements, there are also impressive new results, but not really the result that will provide an ultimate answer to the problem. So from a theoretical point of view, we are a bit stagnating. From the computational point of view, also have to say, in the sense that, as Giovanni was mentioning before in this very beautiful landscape, the techniques that we're actually using are still based on large eddy simulation or variational multiscale methods that were developed at least 10 years ago, not to say 20 years ago. And so it seems that there are no really new breakthrough advancements, neither in the theoretical, in the computational arena. And this might be justified by the fact that with the modern supercomputers, with the existing tools, we are in any case able to address not all physically relevant problems, but an increasing number of relevant problems in applications. So I have to say that we could be somehow relatively satisfied on the basis of the tools that we already have. Of course, the frontiers now is set by the computational time, as you are saying before. If we address problems of higher complexity, we need more computational time. If we want to explore the variability or the uncertainty, as Francesco was saying before, we need repeated solutions. And this is this has triggered the developments of reduced order models, which stand at the core of the AROMA project. And also the data assimilation that were mentioned before. And generally speaking, this is triggering the interplay between physics-based models, like those that we are using, and machine learning-based models. We have more power for visualization, and therefore we have the possibility of acquiring high-quality data. And we have the possibility of training networks on a big variety of experimental data or numerically produced data. And I believe that this will also help the development of theoretical understanding of the subject. Because the more you compute, the more you see, the more you understand the physics subtleties of the fluid behavior. And this might be something that will eventually trigger the development of the theoretical achievements. So we are living in a kind of transient phase, like if you use the terminology that we use in fluid dynamics. This is a kind of transient regime between basic discoveries and new, which are based on mathematical understanding, pure mathematical understanding and physical understanding, and new discovering that will be enabled by the possibility of using computer on more and more interesting, more interesting mathematical problems and physics problems that will shed new light on the basic understanding of fluid behavior, and therefore will, I hope, provide new stimuli to fundamental research to progress. So it's one of the those periods in the life where experimental analysis, which is now mostly based on computational analysis, will help the development of theoretical analysis. This is what I believe.
No, thanks a lot, Alfio, for this visionary view, since I think that it's in the spirit of also this forum. Is there a question from the audience?
Oops. Yeah. Thank you. I'm Martin Andler. I'm a mathematician, but pure mathematician, so I really... 25 years ago, I talked to Pierre-Louis Lyons just after his Fields Medal, and one thing that he told me is that many results in computational fluid dynamics, he just didn't believe them. He didn't believe that the results obtained by computers were correct, that the codes were correct. So it raises a question, because if the simulation is wrong, then the insight on the theory is wrong. So Luigi Cartenone, you said that a lot of progress has been made in the last 20 years. Could you maybe a bit elaborate why now you believe that the results coming from simulations are correct, and maybe 25 years ago they were not correct?
Okay, so first of all, if Pierre-Louis made the statement, we have to be extremely respectful of the statement. On the other hand, it's true that things evolve, right? So let me make a comment. Again, it's a personal comment. 25 years ago, 30 years ago, 20 years ago, most of the existing commercially available CFD codes were developed by engineers. And this is not a negative remark, it's just a remark, right? So engineers, computational physicists, have a lot of intuition. They know the problem. So they always end up with something which is somehow physically motivated and justified, right? So let me say, I'm a bit exaggerating, but let me say that the codes existing 25 years ago, 30 years ago, were codes that were validated on many applied examples, but often they lacked of real numerical theory. It was too early, basically, right? You know, research advances with different legs. We made one step, and then which is based on experimental evidence, for instance, or intuition. And then the second step, you try to provide a theoretical justification of this first step, right? And then by developing this theoretical insight, you may see something that allows you to generalize and make a further step. And then this will be validated by numerical experiments and so on and so forth. So they're never really completely aligned, right? So 25 years ago, the computational experimentation, say, let me call it this way, were much ahead of numerical justification. Now, numerical justification today has made substantial progresses. As you know, numerical analysis is based on very strong pillars: consistency, stability, convergence. So these are dictated by theoretical results, right? So today we understand much more than what we understood years ago. For instance, we know that finite volume methods that stand at the very basis of the most popular CFD codes worldwide can be regarded as examples of discontinuous Galerkin methods, which are based on very strong theory now, right? So now with this type of theory, we can justify what 25 years ago we could not justify. So this is a long story to say that we can be much more confident today that the codes that we are using, we are aware of their potential also in terms of theoretical properties. So we have a better mastership of the code that we are using. And say in parallel, engineers have become much more aware of the theoretical properties of numerical methods that they are using. So in short, we can be more confident on what we're producing today with respect to what we're producing 20 years ago, 25 years ago, with the state-of-the-art codes that were available 25 years ago. This is my personal opinion.
Thank you, and also this is, we support, of course, also with experience, your personal vision. So it's shared in the also I think in the audience and other my group. So we move on. Thanks, Professor Quarteroni, also for this further, let's say, tough on advance in computational software. And now we go more on the application aspect. The first one is presented by Maria Strazzullo, fast and reliable parametric solution in environmental sciences. Maria, please.
Good morning, everyone. I'm Maria. I am a PhD student in SISSA, and today I'm going to give you a brief overview about my research project on fast and reliable solutions for environmental sciences. So let's start from the meaning of environmental sciences. Environmental sciences mean basically forecasting and predictions. And the main motivation is about monitoring and manage possibly dangerous situations. I don't know, like pollutant release or climate changing, hurricanes, tsunamis, and so on and so forth. And in order to do that, basically you need simulations. Parametric simulations, because you want to actually study the phenomenon under different point of views, different physical or geometrical features, but actually your simulation in this context must be also very similar to data that are collected in situ. So the mathematician, in this case, it's not enough and has to collaborate with other experts that basically have to join their knowledge about physics and about information on data that are in situ. For environmental sciences, you need actually two kinds of experts. The one that gives you the simulations and the other one that basically interprets your simulation about its knowledge about the phenomenon. And this is the reason why we joined our effort with OGS. OGS is the National Institute of Oceanography and Applied Geophysics here in Trieste. And we have an ongoing collaboration with Professor Renzo Mosetti from the Oceanography Research Center. And basically, they were actually interested to put data, their data, in the model. Indeed, on our side, we give them numerical analysis, the parameterized settings, simulations, but them, on their side, they gave us a lot of knowledge about the model that we didn't know, about the data and the information, but still they were not happy with their data because, as you may know, the data are usually difficult to interpret, difficult to collect, and they are scattered. You have to work on it before using them. And actually, as mathematicians, we usually work with models, but models also are not so good in order to interpret the actual reality because, by definition, they are a simplification of reality. And our idea was to put together the data and the model with a mathematical tool that now I try to let you understand, optimal control. I try by drawings, actually. So imagine to have a factory that has to change raw material in order to produce something, okay, let's say money, but the factory produces also pollutant. Now the question is, how can I change the pollutant release in order to stay under a threshold? The threshold in our case is the data. So this is the uncontrolled system, the one without the data inside. Now, if we put the data inside in this new framework, we are able to produce less pollutant, as you can see in the blue circle, basically shrinking the quantity of raw material that we can put inside our factory. So optimal control can be used for several applications, in my case for exactly environmental applications. We will see two applications. One is regional and is about the safeguard of the Gulf of Trieste. And the other one is somehow global, let's say, because it deals with the forecasting of currents of the Atlantic Ocean. Let's start from Trieste. We know that Trieste is a city that is one with the seaside, with the Adriatic Sea. It overlooks the sea. So basically all the economic feature, the community, the tourism, the social life is linked to the seaside. And this was basically the reason why OGS was really interested in studying the Gulf of Trieste and its safeguard. So our simulation, it's a very simple simulation. It's about the control of a pollutant release. So we imagine basically that a pollutant loss was in front of the city of Trieste, and we want a safeguard threshold in the naturalistic zone of Miramar. And I don't want to be much detailed, very detailed on the simulations, but you see, if you see the red dot, basically it means danger. So the simulation on the top is the one without data and the threshold is not verified. Inserting the data about the threshold, we were able actually to decrease the quantity of pollutant and so to maintain the threshold in the Miramar zone. And we studied this phenomenon for several parameters that were indicating the wind blowing on the Gulf, so Bora, Scirocco, and this is the result for Bora, for example. Another experiment that you can do basically is to understand how the water moves around the shores, around the bays, and this is actually the main topic of coastal management. Coastal management is growing because actually, you know, all the economy, social life, tourism, also anthropic behavior is linked to coasts in this particular context, like harbors or also, you know, beach and so on. and so on. So basically you want to understand how the waves moves in the shallow waters. And I am showing here a really simple example. This is actually a drop of water, basically moving in a pool. And you can see that in even this very simple example, there are a lot of little waves, a lot of oscillations that actually you don't want in a real application like harbors, and you don't want a lot of waves on your ships, for example, or on your coast for erosion. So putting data inside could help in order to remove this kind of oscillations. The last application is about the forecasting, weather forecasting. Basically here we wanted to reproduce previous data simulation that you can see on top. On top basically there is the representation of the Gulf Stream. So here the current is going from west, that is the Florida Peninsula, towards northeast, so Europe. And putting the data in our model, we were basically able to reproduce quite well the behavior of the Gulf Stream, and we studied this phenomenon for several parameters that could represent seasonal movements in the ocean. And the model that we use is a coupled surface and atmosphere model that actually is used to understand hurricanes. So this could be really useful in order to predict catastrophic events. So concluding, I want to share a message with you that is basically that collaboration between scientists is very important, and for sure taking into account data in order to make models more precise for environment is for sure important, because environment means a lot of things like social life, touristic life, economy, activity, and so on. And basically mathematics can be useful for the whole community of a marine city like Trieste. Thank you.
Thanks, Maria. And now we switch to another application field, which is cardiovascular flows, with Zakia Zainib. Zakia is a SISSA alumna, and now she's at Technical University Eindhoven, and she's connected from Eindhoven. Zakia, I do think that you can change autonomously the slides. No? Okay, I will do for you.
No, sorry, I can't. Hi, good morning. Thank you, Gianluigi, for the kind introduction. I'm Zakia Zainib, and today I'm speaking at this platform as a collaborator of SISSA MATLAB. So I'm going to show you the utilization of reduced order methods in biomedical industry, especially in the cardiovascular applications. So far, we have seen the computational efficiency of these techniques, and Maria just showed us that these methods, when applied with optimal flow control, can be used to govern, to control, to forecast certain physical phenomena. And I will show that in the cardiovascular application, this can help us move one step forwards toward the patient-specific data assimilation. Next slide, please. So before starting, a little introduction about me. I'm originally from Lahore, Pakistan, where I did my bachelor's and my master's. Then in 2015, I moved to Trieste to have a PhD in mathematical analysis, modeling, and application with the SISSA MATLAB group. And since February 2020, I'm working as a postdoc researcher at Eindhoven University of Technology. And what I'm going to talk about today is my PhD research work carried out in collaboration with Professor Rozza, Dr. Bellerin, and the external collaborators from University of Toronto and Sunnybrook Health Sciences Center in Canada. So let's start with the first understanding the medical side of the problem. We specifically dealt with coronary bypass grafting, where coronary arteries are small vessels connected to outer side of heart walls having a diameter of few millimeters. They carry oxygen-rich blood to heart muscles, and this blood supply can be partially or completely blocked if these arteries develop plaque. So the surgical treatment for such a problem is to extract blood vessels from other parts of human body and to connect to the blocked arteries after the point of blockage. And at this point, the medical doctors are interested in keeping a track on how these externally grafted vessels are behaving after the surgery in a non-invasive way. Next, thank you. So at this point, the mathematical part intervenes in form of mathematical modeling, data assimilation, and computationally efficient numerical techniques. Assume that for a single patient, the clinics have medical images in form of, for example, 4D MRIs or CT scans. These images incorporate important information about the behavior of blood flow, about the structure of the blood vessels. And the mathematical setup consists of incorporating this information into an appropriate mathematical model and simulating the patient-specific hemodynamics. At this point, one can study several phenomena, for example, the identification of restenosis, its location, its extent, if it is there, or the quantification of the flow conditions that can affect the behavior of the hemodynamics, or filling in the gaps between the data that is provided. Or we can also help surgeons to decide on what is the optimal design for the grafting procedure. So the goal here that we had was to set up a numerical pipeline to model the patient-specific hemodynamics in a fast, reliable way in the many query parameter-dependent scenarios. And one has to notice that this is not a single discipline project. Instead, it's a multidisciplinary collaboration between surgeons and radiologists who can attain this kind of medical data and can read it, between the image processing information, engineers and biomedical engineers who can attain who can extract the information from these medical images and provide it to us. And then between biomedical engineers, software engineers, and mathematicians who can choose the appropriate mathematical model, the flow conditions, assimilate the data into that. And in the end, previous slide. And in the end, simulate the patient-specific hemodynamics. Next, please. So for this work, we collaborated with Dr. Fremus and Dr. Lara Jimenez-Juan from Sunnybrook Health Sciences Center in Toronto, in Canada, and with Professor Piero Treverio, who is at University of Toronto in the Electrical Engineering Department. Next, please. Okay, so the data simulation consists of two types of data. One can be related to the geometry of the problem. The other can be related to the physiological behavior of the fluid flow. So for the geometrical, extraction of geometrical data, we use the CT scan, and the extraction can be done by using multiple software, for example, VTK, VMTK, or ParaView. And it's a hands-on, hands-off experience. For example, in this figure that I'm showing you, we extracted this geometry from a CT scan for a triple coronary bypass graft. And the occlusion can be seen in the marked circles in the first obtuse marginal artery and left anterior descending artery. And right internal thoracic artery is grafted, and another graft is done using the venous vein to bypass the blockage in the blood flow. This type of data can then be incorporated in our mathematical model as our computational domain. It's discretized, and a volumetric mesh has been created on this. Then the next part is, do we have any information about the physiological flow? Well, for the cardiovascular problems, we can use 4D flow MRIs. They can provide us information about the volumetric flow rate of blood in some part of or some region of such sort of a geometry, or blood flow velocity. And we can assimilate this data into a problem as the difference between this data and what we expect our simulation to achieve. Then the goal is to simulate the patient-specific hemodynamics such that this difference is almost negligible, so that our mathematical simulation represents a real-life scenario. And in doing so, we can control several things. For example, the data is not always complete. We cannot exactly get the information about the flow conditions at the outlets, and this can be quantified automatically using this framework. Next, please. So these are the cardiovascular problems. The mesh has to be discretized finely enough to have a reliable simulation, and this can take much time. For example, for our simulation, it took in the non-parameterized second, it took 30 minutes. The question then is that if we are in parameter-dependent scenarios, do we have to spend 30 minutes every time the parameter changes? Next, please. The answer to this is no. Thanks to reduced order methods, we don't. We can divide our procedure into offline, online, where the heavy calculations are performed in the offline phase, performing only once, and then we are left with having to repeat only the online phase, which can be performed on your personal laptop. So for the example that I showed you, we were able to reduce the time from 30 minutes to only 3 minutes. And the good thing is that the offline phase can be taken care of separately at the supercomputers, while you only need your personal computer to perform the online one. Next, please. And this is particularly beneficial because our next goal can be to develop an algorithm where if we have a clinical database of patient-specific data, the supercomputer should bear the heavy load of the calculations, and then resultingly, the medical doctor should be able to have the fast results obtained online on their personal laptops or tablets or mobile phones. And this is a work in progress. Thank you.
Thanks, Zakia. So, we are perfectly in times. Now we have the last 3 short communication of 5 minutes each to end the session. And now I would like to call here at the podium Monica Nonino, giving an overview on fluid structure interaction.
Good morning to everyone. I am Monica Nonino, a 4th-year PhD student at SISSA MATLAB Group, and as Professor Rozza mentioned, my research focuses on reduced order methods for fluid structure interaction problems. So the main goal of my work is to develop and implement algorithms that can provide, in a short amount of time and by using a small amount of computer memory, reliable simulations of very complicated problems, such as fluid structure interaction problems. So let me start by saying that in general, fluid structure interaction has a wide range of applications. Indeed, for example, in aeronautical engineering, with FSI, we can model the interaction between the air and the wing of a plane. In naval and nautical engineering, we can model the interaction between the water and the hull of a ship. But most importantly, FSI has a fundamental role in biomedical applications. Indeed, with FSI, we describe the behavior of the blood flow in human arteries, and we describe how the leaflets bend under the blood flow, for example, in a vessel in the human body. So let me give you a practical example of a problem that I have been working on. So as you can see, here we have a 2-dimensional section of a vessel in the human body. And in red, you can see the leaflets, whereas in blue, you can see the part of the vessel where the blood flows. In this problem, we have 2 parameters, so 2 quantities whose values we can change. The first parameter represents the length of the leaflets, whereas the second parameter represents, in some sense, the softness of the biological tissue by which the leaflets are made of. Now the question is, how do the 2 leaflets bend under the blood flow? And what happens if we play a little bit with the different values of the parameter? And how can we obtain these answers in a fast and reliable way? So the first thing to do is to move from the words to the mathematics, meaning that we move from the problem of interest to a system of equations that models the problem that I just described. Then we develop and implement an algorithm, which is the key tool that allows us to move from the system to the actual results. So, for example, here at the bottom of the slides, you see an example of the behavior of the leaflets for 3 different values of the parameter μg. So, the longer the leaflets, the bigger the deformation. To obtain simulations of problems that arise from the biomedical applications, it takes a lot of work. So we start with clinical data that doctors provide us, that usually are CT scans and MRI. And the first thing we do is we move from the clinical data to actual data that we can give as an input to the algorithms. We also develop and implement these algorithms. And it is important to mention that very often we rely on machine learning techniques, especially when we have to handle very big data sets, for example, using neural networks. So the mathematics behind the fluid structure interaction problems is extremely complicated. And so it takes a lot of effort to go from the starting point, which is the mathematical problem of interest, to the final point, which is, for example, in this case, the simulations that we are going to provide the doctors. And this passage is possible thanks to the collaboration between different professional figures, such as mathematicians, engineers, and in this case, doctors. So, to conclude with this presentation, I just wanted to show you very briefly how fluid structure interaction is a very wide and interdisciplinary field of research. And this is fundamental because it underlines the fact that mathematics is a fundamental aspect that contributes to problems in everyday life. And with this, I thank you for your attention.
Thanks, Monica. Thank you. So now we switch to Martin S. Thank you.
Yes, hello, my name is Martin Hess. I'm a postdoc also in the SISSA Math Lab group, and I'm also being employed on the ERC AROMA-CFD project. What I'm going to talk about is spectral element computations, which are some highly accurate method of numerical discretizations and some particular applications. But first, briefly about me. So I did my education in Germany, and I also come from Germany, including PhD, and I came to Trieste in December 2016. I must say that I quite like it here in Trieste. So you can see one picture which shows that Trieste is as well as at the sea as at the mountains, and it gives you really ample opportunities for all kinds of sports. Now I know that this is a little bit mean of saying that right now, because I know most of you can't be here, but maybe you will have a chance to come into the future. So what would I like to talk about? There's a particular effect called the Coanda effect, which is a physical phenomenon which is maybe not so well known, which I would like you to understand in this brief talk. And I will give you an interesting example of a NOTAR helicopter, which is a type of helicopter which maybe you're not familiar with. Then I will say what this has to do with pitchforks, and then just very briefly about what are spectral elements about. So the Coanda effect. Imagine you have got a jet flow which is streaming out. Can be fluid, can be gaseous. This jet flow is a high velocity flow, which means that it's going to create low pressure areas on top and below this jet flow, which is going to suck the surrounding air in the direction of the flow. Now, if you have got a wall on one of the sides, that means that the pressure there is even lower, and the ambient pressure from the top is going to push the flow down towards the wall. So what you can see is that what is called Coanda effect is that as long as you have got a convex surface, the flow is going to attach itself to this surface. So what does convex mean? Here you can see a convex curvature. It means basically that the wall is bulging into the direction of the flow. On the other hand, there can be corners, which are non-convex walls, and in these cases you will get low pressure vortices, so like rotations. Another example is the mitral valve in the human heart. So in the blood flow, in internal flow dynamics, you can also observe these Coanda effects within the blood vessels of, for example, the human heart. But just briefly about the NOTAR helicopter. NOTAR stands for no tail rotor, and you can see that the back, the tail of this helicopter looks very different. So how does it steer? How does it work actually? It uses the Coanda effect for steering, and I would just like to very briefly explain how it works. So imagine a helicopter, and let's look first maybe at the picture below here, 6, 7, 8, these numbers. This is a cross-section of the tail, and you can see indicated by 6, the downwash from the main rotor. So the main rotor is rotating in a direction, counterclockwise, clockwise, either one. And it means that the flow coming from the main rotor is a little bit asymmetric. So the flow is going to attach itself first to the surface of the tail cross-section, but in a non-symmetric manner. So that means the flow velocities will be different on the left and on the right side, and the pressure will be different. That means there will be a resulting force, shown by this green arrow, number 8, which is going to push the tail to one of the sides. Maybe you've seen this sometimes in an action movie. If the tail rotor is being destroyed of the helicopter, and then the helicopter is going to start spinning. So to counter this effect, there exists a fan inside the tail, which is going to push air into the tail. And then you can see these red arrows here, that there are little holes in the tail which are built asymmetrically. And by changing the pitch of the inner fan, you can actually control the flow which is being pushed out here, and this can counter the effect of the main rotor. So in effect, you will be able to steer your helicopter left and right. Here you can just see how the flow inside the tail is occurring, and there's an additional anti-symmetric or non-symmetric outflow at the very end. Now, we do simulations to be able to understand better exactly how this effect occurs. So here you can see a channel flow with a jet emanating from one side, and you can see two solutions for exactly the same configuration. And this is also a difficulty from the mathematical point of view, because you don't have got uniqueness anymore, but you do have got multiple solutions for the same model configuration. Now, if you do many simulations for this model, you can actually see that what appears is a pitchfork. So you have got two solutions, one time hugging the upper wall and one time hugging the lower wall, which are stable, and you have got a so-called unstable solution in the middle. That unstable means this only exists mathematically. You will never be able to observe this in nature, because a tiny change, a tiny perturbation to model parameters will make the solution go to one of the stable branches. In order to resolve these field solutions, we got high-order polynomials. So here you can see, for example, the first 5 Legendre polynomials. And this is also being published in our open source software framework, ERC. Now, research-wise, there are really many questions related to this, like if the method is stable, if it's efficient, how fast does it converge, can you estimate the error? This is a wide field. These are difficult questions, and this is what we work with every day. But I will not go into it here, but I would like to thank you for your attention.
We are transitioning to the last but not least speaker, introducing an aspect of the AROMA-CFD project called FARE. We are devoting our attention also to compressible flows, thanks to a top-up project that the Italian government decided to give to ERC grantee in order to attract ERC grantee from abroad, or to just avoid that ERC grantee could move from Italy to other countries. So, Andrea Lario. Thank you.
Hello, everybody. My name is Andrea Lario, and I'm a postdoctoral research fellow at SISSA MATLAB. Okay, today I moved to Trieste a couple of years ago after a PhD in aerospace engineering at Politecnico di Torino. So today I'm going to give you a very brief overview on the FARE per AROMA-CFD project, which is basically an extension of AROMA-CFD project, but this time it's funded by the MIUR, which is the Italian Minister for Research and University. As Gianluigi has just said, FARE was an initiative of the Italian government in order to give to young researchers the possibility to stay here in Italy. In particular, in FARE per AROMA-CFD project, we had two main goals. The first goals, it was the development of reduced order models for compressible flows, and the second goals instead is related to the reduction of the space of parameters. So you have already seen this slide in Giovanni Stabile's presentation, but just to give you an idea what we are talking about, we are now dealing with compressible flows. So we are on the bottom left side in the red circle, and the main characteristic which distinguish the compressible flows from the incompressible ones is that basically the density variations are not negligible anymore. So in order to keep this variation into account, we have to add an additional equation, so the structure of our system of equations changes a little. On the right side, you can read the additional equation, again in the red circle. So, compressibility effects becomes important when high-speed flows are considered. So, these fields are particularly relevant for applications which are related to the aeronautical fields, but also for applications which are related to the so-called premium automotive field. For example, Formula 1 car, racing cars, but also the so-called hypercars, because now they can exceed a top speed of over 400 kilometers per hour. So compressibility effects are also important to consider. Both in aeronautic and in premium automotive applications, the final product must have some very high performance. So the optimization process is absolutely fundamental. So it could be a good idea to extend reduced order modeling techniques also to compressible flows. But unfortunately, we cannot really take the already developed reduced order models which we have developed for the incompressible cases, since we would end up with an unstable system of equations. So we have to develop new techniques and new strategies in order to end up with a stable set of equations. That was the first task. Briefly on the second task, instead, in many problems of practical interest, for example, optimization, but also shape design, morphing, and so on, we have a lot of parameters to take into account. For example, we want to optimize, in terms of drag reduction, the shape of the hull, which is depicted in the picture on the top right of the slide. And for example, in order to do that, we have to consider physical parameters, we have to consider geometrical parameters, and so on. The problem is that the higher is the number of parameters, the higher is the computational cost that we have to afford in order to have a robust optimization. So the question is, can I reduce the number of parameters? And there are some techniques based on active subspaces which can give me very useful information about that. For example, they can give me the information that some of the parameters that I was initially considering are actually negligible, or they allow me to rotate the space of the solution, and looking to my problem from a different perspective, I can discover that my problem is much simpler than I thought at the beginning. For example, in the picture in the middle, at the beginning, I have a results seems completely scattered, but if I rotate the space, I discover that that's a parabola, basically, so much easier to model. So this was a very brief overview of FAR-EPER AROMA-CFD project. All the techniques which I have described have been implemented in Ithaca DG for the compressible part, and Athena instead for the problems related to the reduction of the space of parameters. I was the last speaker, so I'll let you with the photo again with the Rozza group and all the contacts information with the website and the Twitter if you want to follow us. Thank you.
Thanks, Andrea. We are a little bit over time, and I think that in 1 minute the streaming also will be interrupted because there will be a following session. So I would like to thank all the speakers, of course, but especially I would like to thank our special guest, Professor Alfio Quarteroni. And Alfio, maybe if we have just a few seconds, you can advertise your virtual session in medicine, such that there are already topics that have been introduced, and maybe you can invite people to attend your session, since I had no time to ask you a question in medicine.
Okay, thank you very much. So this will be this afternoon at 6 p.m. in virtual room number 2, and I will talk about the integrated art model, which is a mathematical model to try to simulate the complete heart function. But I would like to thank you for giving me the opportunity to follow this very interesting talk, and to congratulate you to all your brilliant young collaborators.
Thanks a lot. And I want to thank also all people attending in streaming and in presence. And so have a nice continuation of the European Science Open Forum and have a nice day. Thank you all.